Another day, another story. Nuclear fusion occurs when two atomic nuclei join together to form a heavier nucleus, releasing energy as a result. Ignition, in this context, refers to the point at which a self-sustaining, controlled nuclear fusion reaction is achieved in a laboratory setting. This is a major milestone in the field of nuclear fusion research, as it demonstrates that it is possible to generate significant amounts of energy through this process. However, it is still a very challenging and complex process, and there is much work that needs to be done in order to make fusion a viable source of electricity on a large scale. On December 5, scientists at the US National Ignition Facility, NIF, successfully achieved ignition, or a nuclear reaction that generates more energy than it consumes, at the world's largest nuclear fusion facility. This exciting development, announced by the US government on January 8, has garnered attention from the global fusion research community as it has the potential to provide a virtually limitless source of clean energy on Earth through harnessing the same process that powers the Sun. The achievement is the result of years of work from various teams on various components, including lasers, optics, targets, and computer models. Mark Herman, the Deputy Director for Fundamental Weapons Physics at Lawrence Livermore National Laboratory in California, where the NIF is located, described the accomplishment as incredible. The U.S. National Ignition Facility, NIF, a flagship experimental facility of the U.S. Department of Energy's nuclear weapons program, has faced criticism in the past for delays and cost overruns in its mission to study reactions created by nuclear weapons and achieve ignition by 2012. In August 2021, NIF scientists announced that they had achieved a record reaction using their high-powered laser device, but were unable to replicate the experiment in the following months. As a result, the team decided to change their experimental design, which ultimately led to their successful achievement of ignition on December 5, 2021. This accomplishment has been celebrated by fusion researchers, including Michael Campbell, former director of the Fusion Laboratory at the University of Rochester in New York and an early supporter of NIF. What did NIF achieve? The US NIF used its array of 192 lasers to deliver 2.05 megajoules of energy onto a small gold cylinder containing a frozen pellet of the hydrogen isotopes deuterium and tritium. The high-energy pulse caused the capsule to collapse, creating extremely high temperatures and causing the hydrogen isotopes to fuse into helium, releasing energy and triggering a chain reaction of fusion reactions. Analysis from the laboratory suggests that the reaction released approximately 3.15 megajoules of energy, which is about 54% more than the energy that was put into the reaction and more than double the previous record of 1.3 megajoules. This marks the first time that fusion has produced more energy than it consumed in a laboratory setting, according to Campbell. The recent experiment at the US NIF safely met the criteria for ignition, a key benchmark in fusion reactions that compares the amount of energy put into the target to the amount of energy released. While the fusion reactions did produce more than 3 megajoules of energy, which is more than the energy delivered to the target, the NIF's 192 lasers used a total of 322 megajoules of energy in the process. Despite this milestone, NIF is not yet a viable fusion energy device and there are still many steps to be taken on the path towards laser fusion energy, according to Dave Hammer, a nuclear engineer at Cornell University. The NIF team made several changes to their experimental design and laser power before the latest successful shot, based on analysis and computer modeling of previous experiments. Why are these results significant? The recent success of the US NIF in achieving ignition has been celebrated as a significant milestone in fusion science, and it also holds particular importance for NIF as the facility was designed to study the heat and pressure of thermonuclear explosions, which can only be done if the facility produces high-yield fusion reactions. It remains to be seen what the U.S. Department of Energy will do next, as it could continue to focus on weapons research at NIF or shift its efforts towards a laser program specifically geared towards fusion energy research. What does this mean for fusion energy? The recent breakthrough at the US NIF has sparked interest in the potential for clean fusion energy, but experts caution that there is still a long way to go before it becomes a reality. While NIF was not specifically designed for commercial fusion energy, its success could increase confidence in the potential of laser fusion power and potentially pave the way for a new program focused on energy applications. However, significant engineering challenges remain, including the creation of plants that can extract the heat produced by fusion reactions and use it to generate significant amounts of usable electricity. There are also ongoing fusion experiments worldwide that are attempting to achieve fusion for energy using different approaches. While the recent success at the US NIF is a promising development, it is still far from the level of energy gain needed for the production of electricity, according to Tony Rollstone, a nuclear energy researcher at the University of Cambridge. However, Anne White, a plasma physicist at the Massachusetts Institute of Technology, believes that the NIF's experiments on fusion energy are valuable in the pursuit of commercial fusion power. What are the next major milestones in fusion? The NIF is studying a type of fusion that has the potential to be a source of energy, but there are several challenges that need to be addressed in order to make it viable. One of these challenges is improving the efficiency of the yield, or the amount of energy released compared to the energy used to create the laser pulses. In addition, the rate at which the lasers can produce the pulses and the speed at which the target chamber can be prepared for another burn must be increased. Another project, the International Thermonuclear Experimental Reactor, ITER, is also working on developing fusion as an energy source, but using a different approach called tokamak confinement. ITER's goal is to achieve self-sustaining fusion, where the energy produced by the fusion reaction is able to maintain the reaction itself, which is key to producing more energy than is put in. The ITER project is expected to reach the burning stage, where self-heating power becomes the primary source of heating, in 2035. Thanks for watching.